Yeah, we are live. You can start.
Okay, awesome. Thank you. So thank you everyone for coming. Thank you, Devendra, for setting all of this up, and Ganesh for dealing with all of the live streaming and technology issues. Today we have Levent Alpoge, who will talk to us about modularity and effective Mordell. And yeah, so I will hand over the mic to you.
Thank you so much. Thank you. And yeah, don't worry about the inconvenience. I manage to mess up technological things all the time. Hopefully that when I go through the slides, I won't accidentally close them or something. So anyway, yeah, thank you so much for the invitation. I've still never been to India, but this is the kind of closest. I guess I'll count this a little bit as Epsilon being to India. So anyway, thank you so much for the invitation, and it's really a pleasure for me to speak in this special year. So I will be talking about the Mordell conjecture, finding rational points on curves, and how to use modularity. And I will really get to talking about triangle groups and hypergeometric family varieties and Belian maps and things like that later on in the talk. They really appear, so I'm kind of excited to get to that point. So yeah, let's get started. So it's a little bit corny, and maybe if you've been to a previous talk of mine, it's getting old, I don't know, but I like to start with this quote found by, or left for posterity by the Byzantine scholar Hortasmenos in about 1400 AD. When he was reading Diophantus's Arithmetica, he got to the problem, I think, after the one that inspired Fermat's last theorem, the conjecture in Fermat's reading. And he was frustrated. Diophantine equations are tough, and he decided it was time for him to write some angry doodles in his book, which amusingly happened to have survived for hundreds of years after, and now we can giggle about them. So anyway, this is what he had to say about Diophantus when he was reading the Arithmetica. And I start with this just as a reminder that Diophantine equations are tough, and even if you're a Byzantine scholar. So okay, so the theorem maybe that I have to start with, or it's prudent to start with, is the theorem of Matyasiewicz, building on work of Davis, Putnam, and Robinson, which goes as follows. So Hilbert asked in his 10th problem in his list of Hilbert problems, if there's some kind of mindless procedure that if you want to figure out, does this some particular equation have an integer solution, you just kind of turn the crank, and eventually, if you wait long enough, you'll get an answer yes or no, and you'll be able to tell whether or not you have a solution. So Hilbert asked with the expectation that there would be such a mindless procedure. Let me call that algorithm. And for the rest of the talk, by algorithm, I mean Turing machine. So Hilbert asked, is there an algorithm which terminates on every input and tells you the correct answer on every input, and given the input of a polynomial, and at least in arbitrarily many variables, returns true exactly when that polynomial has an integer solution. So the famous theorem Matyasiewicz, building on work of Davis, Putnam, and Julia Robinson, is that at least in sufficiently many variables, if you're asking for solutions of polynomial equations over the integers in at least, I just put 26 as a particular example, in at least let's say 26 variables, then there is no finite time algorithm that will determine whether or not a general input polynomial equation has an integer solution. So kind of this is an impossible thing to do in sufficiently many variables and sufficiently high dimension. Let's think about it like that. Yeah, so this is an impossibility result, counter to what Hilbert expected. It's believed. The whole talk is going to be about some kind of possibility. So let me explain why I started with this theorem. So this theorem says that in sufficiently many variables, so to speak, it's impossible to determine whether or not an equation has an integer solution. However, if you're in one variable, it's trivial to determine whether or not a polynomial equation in one variable has a solution. For example, whatever it's called, rational root test or something. Imagine you have an irreducible polynomial in one variable, let's just say, then whatever integer solution f of x equals 0 you have, that integer must divide the constant term. So anyway, that cuts you down to a finite set. So there's a trivial algorithm when you're in one variable. This was known, to our oldest ancestors, I guess. But and I said in 26 variables, just as a particular constant, there's no possible algorithm, and it's expected that there will be no, so to speak, effective solution to the problem when you're in at least 3 variables. So kind of you're impossible in at least 3 variables, maybe for logic reasons. We will see when this theorem is proved eventually. And it's possible in 1 variable, so that leaves naturally the question of what happens in 2 variables. So to speak, what happens for equations of curves and integer points on curves. Okay, so the relevant theorem that I'm going to be talking about today is the great theorem of faultings, which says that if you give me, so this was before about integer points, but now I'm just going to jump to rational points. So the theorem of faultings is that if you give me a smooth projective hyperbolic curve, hyperbolic meaning genus bigger than 1, curve over a number field. So just to always have an example in mind, if you give me the curve of y squared equals x to the 6 plus 1, let's say, over a number field, then it only has finitely many rational points over that number field. So there's only finitely many solutions to this equation over any number field. So for example, over Q, but it's actually pretty easy over Q to see this, but over Q adjoin I and Q adjoin zeta 128, for example, has only finitely many solutions. So yeah, so that's the theorem I'm going to be talking about. Now, this is a great theorem. It's I guess actually I think the conjecture is 100 years old this year. Conjecture of Mordell, stated in a paper in 1922. And the theorem was proved after, I think, like 61 years eventually by faultings. And it's a incredible theorem, and it has actually a number of proofs now. And unfortunately, all the proofs that are known tell you that this equation, for example, has finitely many solutions over a number field, but they tell you nothing about the solutions. They give you no way of actually determining that finite set of solutions. And I guess this is a point maybe I should have made up here, but kind of when you're reading, if you're reading like the old great number theorists, most of the time you're not dealing with equations in 26 variables, or maybe even, okay, there are certainly plenty of equations in at least 3 variables, but kind of most of the time you're dealing with equations maybe in 1 variable in the really old writings, or in 2 variables. So somehow, yeah, it's a very classical thing to want to be able to solve equations like this in 2 variables, as in to find rational points on curves. So anyway, that's kind of my motivation. But anyway, it's a very natural question to ask: can I actually solve this equation? Or maybe I just to keep things over Q for concreteness, can I solve this family of equations? You give me a K, can I actually find the rational solutions, the Q solutions to this one equation? Okay, so yeah, so I already said this, but this is the proof of this theorem is famously ineffective. It does not provide a finite time algorithm to find that set of rational points that you're after, that theorem proves is finite. Okay, so you can start with this equation, you go in the proof, and the proof will tell you, you'll be able to run the proof, and the proof will tell you that there's a contradiction in mathematics if there are infinitely many solutions. And actually, it will give you a bound on the number of solutions, but that bound will not be sharp in general. Okay, so yeah, doesn't provide a finite time algorithm to find the rational points on a given curve. And actually, yeah, the situation, I mean, at least to my knowledge, is not so great, even in particular cases. So yeah, there's not so many effective techniques known to solve equations like the one I stated above, y squared equals x to the 6 plus k, let's say. Even over, number fields like Q. So actually, the question I asked, y squared equals x to the 6 plus k over a number field like Q, for plenty of k, we have no way, no kind of general way of solving that equation. We have, maybe I'll call them like ad hoc techniques that will work for lots of k, but but not everybody. And then if those ad hoc techniques do not work, then you just throw up your hands and say, this is a difficult problem. Okay, so there are not so many effective techniques known in special cases. I want to mention really the kind of one that I know and that works in generality, but requires a very strong hypothesis. So I'm going to mention the theorem of Belian and Demyanenko. And this actually, interestingly, I think comes out of work by Demyanenko trying to prove what is now known as Mazur's torsion theorem about elliptic curves over Q. So anyway, it's interesting that it's connected to that. So it says the following. Let me just kind of summarize it a little bit quickly, but over a number field, if you manage, so you're trying to find the rational points on a curve C over this number field. Let's imagine you have Q, for example. So you're trying to find the rational points on y squared equals x to the sixth plus k, but over Q. Just for concreteness. If you manage, so for a particular equation, if you manage to find, let's say, an elliptic curve, so let me call this CK. If you manage to find an elliptic curve, let me just say, with such that there are two maps from CK to an elliptic curve, to the same elliptic curve, and the rank of that elliptic curve is less than is less than or equal to 1. So if the rank of the elliptic curve is 0, kind of you're trivially done. But anyway, so if the rank of that elliptic curve were 1, and you manage to find two maps to that elliptic curve, that is a very strong condition. But if you manage to do it, then the theorem of Belian and Demyanenko and the technique of Belian and Demyanenko says actually there's an elementary way to effectively find the rational points on that curve. But this is an incredibly strong condition, and it will not hold in basically the vast majority of situations that you face. But moreover, it will fail the second that you start taking extensions of your number field, because this is kind of a so this is kind of like the number of independent maps from your curve to, in the way I phrased it, in an abelian variety, or from your Jacobian of your curve to an abelian variety. So this thing is kind of a geometric quantity. It's going to be some bounded thing, even if you start extending the number field. Even if you work over C, this thing is going to be some bounded thing, whereas this is going to blow up. So this will work in very particular cases, but even in practice, it's not really used so much. But anyway, it is an effective technique, and it is really, I think, one of the only ones that I really know for this problem. So anyway, it's important to mention it. So yeah, there's not really that many effective techniques known, and you can see this is a very restrictive hypothesis, I think. So, okay, but I wanted to mention it, and I want to mention somehow I'm really talking about the theoretical issues, namely the issue of, so kind of just maybe it's more familiar, at least for me from an analytic background, it's a little bit more familiar. Maybe I'll indicate kind of the issue that you face theoretically speaking as follows. So there's an analogous issue that occurred in mathematical history, which is there was this problem of Gauss about which imaginary quadratic fields have class number 1. And in that problem, people were able to determine that, okay, we have this list that Gauss conjectured is the full list, and actually they were able to determine that that list is correct up to at most one exception. And that one exception they knew had to be incredibly large and very strange, but they couldn't rule it out. So that's the sort of situation that you face when discussing in the theoretical issues. You face the issue where you can get an upper bound on the number of rational points, and maybe you can find, maybe your upper bound is 12, and you find maybe 10 rational points. But the question is the answer 10 or 12? And at what point, maybe if you work harder, you're going to be able to refine the upper bound from 12 to 11. And the question is, if I work incredibly hard and for thousands of years, will I eventually be able to make that 11 a 10 and get a sharp bound and deduce that I actually only have 10 rational points? Because it looks like, so to speak, I don't have more than 10 rational points, even though I'm searching for a long time. So that's kind of the theoretical issue. But in practice, the situation isn't so bad as I maybe might have indicated. So in practice, there's a theorem of Chaboty, a technique of Chaboty generalized by Min-Young Kim, that says that if you have this hypothesis, which is again one of these hypotheses where you have kind of a geometric quantity on the right-hand side and the left-hand side can blow up, but still this is a hypothesis that's satisfied in tons of examples. Kind of statistically speaking, this is satisfied in plenty of examples. So the theorem of Chapotis says if you have a number field and a smooth projective hyperbolic curve, so genus strictly bigger than 1, curve over that number field, then such that the rank of the Jacobian is smaller than the geometric quantity, its genus, the genus of the curve, then actually you have finitely many rational points. But the technique is ineffective, theoretically speaking. So the bound that you get is ineffective. You get some upper bound on the number of rational points, and there's absolutely no guarantee that that bound is sharp. However, kind of the expectation in practice is if you're working over Q, let's just say for concreteness, if you're working over Q and you have a reasonable curve, you start with a reasonable curve over Q that satisfies the Chapotis hypothesis, which again is really satisfied in plenty of examples, statistically speaking, and certainly in plenty of examples. And then combining the techniques of Chapotis and Mignon-Kim and clever computational tricks, which really should not be underestimated, but anyway, you know, the clever computational tricks in the bag of tricks of the experts. So the expectation is that in practice, if you have this hypothesis, you can hand the equation to the experts, and the experts will actually be able to determine the rational points on the curve. There's not a kind of general technique that's known, theoretically speaking, to always terminate, as in it's not known that the clever computational tricks are always enough. But anyway, this is kind of the in practice expectation. So in practice, the situation is quite good, at least when you have this hypothesis. But theoretically speaking, what I just said kind of requires luck. Oh wait, I should make sure that it doesn't cut off. Yes. So theoretically speaking, what I just said requires luck. So I said that something will require, something is an expectation only. You have some clever computational tricks that you use, and hopefully they suffice. But if they don't suffice, what do? You have to invent new computational tricks, I guess. So it requires luck. The luck really means that you get an upper bound from the technique on the number of rational points, and the clever computational tricks let you refine that upper bound, and then you search for rational points, and you need to be kind of lucky to have those two bounds agree eventually. And actually, this is the situation, theoretically speaking, is not even, maybe it's worse than I'm letting on. I don't know. The point is, actually, there's no known way to compute even the rank. We have this hypothesis. How do we exactly compute the rank of the Jacobian? We don't know how to do that. In my view, the whole point of the Bircham-Swinnerton-Dyer conjecture is to give a way to compute this rank, or at least the whole point of the finiteness of Shah conjecture is to give a way to compute this rank. So, yeah. Anyway, I guess you kind of see this in. So if you imagine you have an elliptic curve over Q, there's a question. So compute. I don't know. How do you compute this potentially infinite set? So let's just say the rank. So how do you compute the rank of the rational points on that elliptic curve? Well, you can try. I mean, in practice, kind of the situation is fine. So in practice, what you might do is, well, okay, much cleverer things than what I'm about to say. But in practice, what you might do is start doing higher and higher 2 descents. So you kind of start computing a 2-Selma group, which you can compute, and then you compute a 4-Selma group, an 8-Selma group, etc. You compute higher and higher 2 descents to upper bound the rank. So those give you unconditional upper bounds that you can compute. And then you can search for rational points on the elliptic curve to get lower bounds. And again, it's exactly the situation where you get a lower bound by searching and an upper bound by doing, in this case, higher and higher descents. And you have to hope that you'll get lucky, so to speak, and the upper bound and lower bound will agree eventually, if you work hard enough. And okay, we know that if you assume the Bircham-Swinnerton-Dyer conjecture, actually, if you just assume the finiteness of Shah of the elliptic curve, actually the 2 primary part, let's say, in the way I described it, then those upper bound and lower bound will agree eventually. But that you have to assume a big conjecture, a very difficult conjecture. But in practice, kind of, you can take those conjectures on faith while you do the computation. But at the end, when the upper bound and lower bound agree, you can conclude that the rank is whatever you computed, and you don't need to assume any conjectures after the fact. but it requires the finiteness of SHA to hold for your particular elliptic curve for that computation to terminate. But anyway, yeah, the computation kind of will terminate if you have faith, and then after that, you don't need to take on faith the result. Okay, so I mentioned that because one natural thing is, so I said, okay, even to compute this one quantity that occurs in the Chapotis hypothesis, you need a huge conjecture, which is Birch's-Swinnerton-Dyer, or anyway, finiteness of SHA. And I said, you have to assume this huge conjecture. So the natural question is, if you assume, so for example, you might ask, oh, what if you assume Birch's-Swinnerton-Dyer? Can you compute the rational points on these curves? And I think, anyway, certainly I think there's no way known to just use Birch's-Swinnerton-Dyer, which is kind of a statement about abelian varieties. But you might ask, like, if you assume everything, every big conjecture kind of, can you compute the rational points on these curves? Can you solve this problem? So it's kind of Birch's-Swinnerton-Dyer lets you get at the rank, but anyway, what can you assume to solve this effectivity question? And the answer, well, one answer is a joint theorem with Brian Lawrence. So there's, let me just put it this way: assume these three very serious assumptions, but standard, very standard conjectures: the Fontaine-Mazer conjecture, the Hodge conjecture, and the Tate conjecture. So if you assume these huge assumptions, but anyway, I'm phrasing it as assume everything, so to speak, not really everything, because you don't want to assume what you're about to prove. So you assume these kind of standard things. Then actually, yes, you can solve this problem. You can find, so there's a explicit algorithm, we write it down, that on input a number field and a curve over that number field, a hyperbolic curve over that number field, will find you the rational points on that curve. And actually the algorithm, I mean, it's not practical at all. Whereas in the case of rank of elliptic curves, it is, that you can really run the algorithm. You go into Sage, you type in, you ask Sage, what's the rank of this explicit elliptic curve? It will answer your question by running that descent type algorithm. Anyway, so this algorithm is not what is the phrase? Impractical in any sense. However, it has the property, the interesting to me property that you run it, and if it terminates, so this a Turing machine. Turing machines don't necessarily all terminate, famously. So I would call this an algorithm, and then I would say, once I know it terminates, it's a finite time algorithm. But anyway, so there's a Turing machine. If that computation halts, then your answer is correct unconditionally. Just like in the case of elliptic curves, when you do this descent thing, you get an upper bound, you search to get a lower bound. If they agree, if that computation halts, your answer is unconditional, even though to know that the computation would halt, you had to take on faith finiteness of some part of the SHA of that elliptic curve. So in this case, if the computation halts, you have an unconditional result. However, to know that the computation will halt ahead of time, you have to assume these big conjectures. Okay, so anyway, I find that interesting. But basically, the upshot is, assuming these big conjectures, yes, you can solve this problem. There is an algorithm. And I want to mention that.
Good question. Sorry.
Of course, yeah.
Yeah. So can you say something about how fast the algorithm is, or like how
it's awful. It's awful. Okay. It requires. Yeah. So one thing that you do is you say choose a prime L and start enumerating all the Galois. So yeah, let me put it like this. So what we really do is we compute. Let me say this line, and then I'll say a word about why one reason why it's very slow. I think that's actually just my opinion. It may be able to run in very small examples, but anyway. So in generality, it will be very slow for the following reason. So what it really does is it really computes this so-called Shafarevich set, which I'm just going to describe as it computes the set of abelian varieties A over K with dimension G and conductor, let's just say conductor at most N. Okay, so and this S will kind of control the conductor by a theorem of Brummer and Kramer. Anyway, so it computes all these abelian varieties, which is, this is a finite set, as proved by Faltings. This is how Faltings proves his theorem. Is he kind of reduces the problem to bounding the size of this set, and then he actually goes and bounds that size. So so one thing that you do, now that I've actually set this notation where I have this S, one thing that you do is you say, okay, consider all fix a prime L and consider all Gauss representations from the Gauss group of Q bar over K to, let's just say GL2G of, I should have left myself more space, sorry. So the Gauss representation will be valued in GL2G of Z mod L to the N. Some huge group, and you start letting grow larger and larger. So this is some huge group, and you consider all the Gauss representations which are unramified outside S. So this is kind of all the extensions of K, Gauss extensions of K that are of degree at most this huge thing, and have what is the phrase? Are unramified. Sorry, are good. What's have are what is the phrase? Unramified. Yeah, are unramified outside S. Good and unramified. Yeah, I have this issue of switching between the two. So anyway, that's a lot of Gauss representation. You're just saying, like, consider all the things of extensions of K of degree bounded by this and discriminant bounded by some huge thing in terms of S. Basically, the product of all the primes in S to the this power. That's a huge set. So and you do this for larger and larger n. So already, it's not looking good. That's just one aspect. There's a number of other aspects, but anyway, this is one thing that I think will lead to leads to issues in the complexity. Okay, so but it did lead me to say this line where what we're really doing is computing this set, so to speak, Shaffer-Average set, and it deduces. So just like faultings, you compute this set, or anyway, you bound this set, and you deduce something about the rational points on your curve by producing a family of abelian varieties over your curve. And I'm going to call this A also, but I shouldn't. So anyway, this Kodaira, there's an old construction of Kodaira, which was observed by Parshin to kind of reduce this question about rational points to this question that faulting solved. And yeah, so you have to produce a family of abelian varieties. I'm only setting this up because I'm going to be talking about a family of abelian varieties in a little bit. So you have to produce a family of abelian varieties to run the argument, and there's a standard construction now due to Kodaira and Parshin. Okay, so that's what I wanted to say about that. The topic today is the topic I'm going to be talking about today is, okay, so this shows you that if you assume everything, if you assume tons of, if you assume the extremely difficult conjectures, take on faith a lot, then the problem is not an issue. But what if you don't take on faith a lot? What if you refuse to assume conjectures and you ask, what can I do unconditionally? It's natural to. So this is kind of like the underlying ideas maybe are here, but I'm not really going to talk about them. But you can ask, like, knowing these ideas, what can you get that's unconditional? And of course, you need some maybe new ideas after that. But the topic is a little bit not entirely going to be about the following thing. So I've phrased it a little bit maybe sloppily. It's actually a little bit stronger than this. But okay, so what I'm going to say is, okay, first off, I said we compute some kind of Shaffer-Average set. This AG, I didn't tell you what it is. I just kind of wrote this notation down. But this is kind of some moduli space of abelian varieties. And I'm taking integer points on the moduli space, this moduli space of abelian varieties. And this theorem is going to be about another moduli space of abelian varieties where the abelian varieties are more restricted. Okay, so the theorem is going to be about, so to speak, Hilbert modular varieties, which I'll give you concrete examples of what they parameterize in a second. But let me just say these are some beautiful family of varieties. And you can ask about the integer points on those varieties. They have very beautiful integral models. And this theorem says that these varieties, which kind of are prudent to ask about because they contain tons of curves, just like this moduli space of abelian varieties contain tons of curves, which allowed you to reduce computing rational points on the curves to. Yes. I'm sorry. I see. Yes. I didn't notice that. Yes, exactly. We do not know all abelian surfaces over Q with good reduction outside too. So it shows you that this question is very difficult, and I think that's So that's the sort of thing. I'm not sure if there's a chance, even if you work over Q, if you run this technique and take on faith these conjectures, the complexity of the argument is such that I don't know if it will terminate in a reasonable amount of time. Anyway, so certainly the way I think about it is not, it's not in a practical way, but indeed it's, yeah, we don't, so let me write A2 of Z1/2. We don't know this set. So this, okay, this includes some kind of principal polarization, which I'm just ignoring, but basically we don't know this set. Thank you for that comment. So that really emphasizes kind of how tough the issue is. Yeah. So, but so what I do want to comment is this is a moduli space of abelian varieties. It's kind of too big. Oh, sorry. It seems my iPad's lagging, but anyway, it's kind of too big you don't have to work with the whole moduli space if you're interested in particular curves. So the theorem I want to mention is the following. So if you reduce the moduli space to a moduli space, let me just write it like this, maybe. So this was the moduli space of all abelian surfaces. You might reduce it to the moduli space of abelian surfaces with an extra endomorphism. Okay, then not just over Q, but over an odd degree totally real field. So this is a hypothesis that comes out of modularity theorems, and actually existence of abelian varieties theorems. But anyway, over particular number fields, where this condition occurs only because this is this current state of our knowledge towards modularity and existence of abelian varieties theorems. Anyway, over these particular number fields, there is an unconditional way to compute the relevant abelian varieties. So I'm going to explain maybe more concretely in a second what this is really computing. So let me just, so hopefully the theorem statement made sense. Over a particular number of fields, if you restrict your moduli space of abelian varieties a bit, then you can actually compute the relevant abelian varieties. So I say, yeah, it doesn't cut off. So hence, you can compute the rational points on curves that happen to map to these moduli spaces. In other words, that happen to admit families of abelian varieties with the property that they're parameterized by these Hilbert modular varieties. I'm going to explain a particular concrete case of what these things are parameterizing in a second. So, okay, so for example, as mentioned, abelian surfaces are already a tough issue. So that an example is there's a way to compute over any odd degree totally real field. This is a hypothesis, again, coming out of modularity and only existing because of our current knowledge and the fact that I want to say an unconditional theorem. So there's a way to compute all abelian surfaces. So all abelian varieties A over K with dimension 2 abelian surfaces with good reduction outside S. In other words, again, by this theorem of Brumer and Kramer, an a priori bound on the conductor of the abelian variety. So already that, if I just assume these two, I'd be dead as far as current knowledge. Even when S is the set of singleton set 2, and I'm working over Q, we don't know how to compute the set of abelian varieties. But if I also assume that there's an extra endomorphism of these abelian varieties, then you can compute these abelian varieties using modularity theorems. Okay, so that's the point I wanted to emphasize. And so because you can, so the reason I don't care so much about adding on this extra condition about having an extra endomorphism is there are tons of curves in the world where you can produce a family of abelian varieties that has this extra endomorphism property. And because of that, is there a polarization assumption? No. Actually, yeah. So maybe the quick way of saying it is, yeah, anyway, no, there's no polarization assumption. So yes, you're absolutely correct that if I write something like this, secretly there are polarizations, but you can compute all the abelian varieties, polarized or not, with this property. And actually, yeah, you can, so to speak, you can, yeah, a priori upper bound. Actually, in this particular case, I don't want to say, anyway, you can certainly a priori upper bound the degree of a polarization on such an abelian variety, so it's not such a crazy thing for me to say, but yeah, indeed, you don't need to, there's nothing assumed about it, like, in this corollary, everything is stated accurately. So you can really indeed compute all the abelian varieties with just these three properties. Yeah, so Okay, so anyway, the reason I don't care about adding this assumption where you have an extra endomorphism is that there are plenty of curves that have this such a family of abelian varieties over them that allow you to run kind of the Partian reduction from computing rational points on your curve to just computing abelian varieties with certain properties. So for example, I like this curve. This x to the 6 is 4 y cubed equals 1, and this curve is going to come up because I'm going to talk about the family of hypergeometric abelian varieties over it, or a family of hypergeometric family of varieties. Yeah, so I say here, the reduction is via hypergeometric family. Okay, so I want to now emphasize this is the point of this talk is not really this slide. This slide is just going to say something if you're to the people who are maybe familiar with these kind of arguments. So the issue I just want to say is the technique, the extra idea is to use modularity to actually compute these abelian varieties, the relevant abelian varieties. And really, okay, so you don't know modularity over these number fields. You don't, so to speak, you don't know modularity over the starting number field. If you start with an abelian variety over that number field, you don't know modularity of the abelian variety. What you know is that there's some extension over which the abelian variety becomes modular. That's some kind of potential modularity theorem. Okay, so I want to kind of emphasize the issues by saying if you knew modularity on the nose, as in if you knew any abelian variety you were facing, so just imagine an abelian surface with an extra endomorphism. If you knew that all abelian surfaces with an extra endomorphism are modular, then they would kind of correspond. Don't worry if you don't understand the words I'm going to say on the slide. So I'm just going to say, okay, so then your abelian variety would correspond to Hilbert modular form over your number field. And it's not an issue because I said odd degree. It's not an issue to produce all the abelian varieties attached to Hilbert modular forms of given level. And the level is kind of given to you because you start with an upper bound on the conductor of the abelian variety. Okay, anyway, so it's not an issue to produce all the relevant abelian varieties by kind of isogeny estimates. And I'm not going to really tell you, what I mean by isogeny estimates, but if you know the kind of Master-Wurstolz isogeny estimate, okay, it's not such an issue because all the relevant abelian varieties are quotients of a single Jacobian of a Schumann curve. That's because I said odd degree. Okay, so yeah, the whole issue. So just this argument is very quick, and the issue is to manage to use only potential modularity. Because this is a kind of technical point if you happen to know how the proof of the Taylor's potential modularity theorem goes, but the technical point is that the proof goes as follows. Well, anyway, the proof produces some extension, and it's hard to say anything about that extension a priori. And you're using, hopefully, maybe this is a clarifying point, but you're searching for the abelian varieties by producing the extensions. So you don't, if you look in Taylor's proof, he will say start with the abelian variety, and this is how you produce an extension. This is the local global principle kind of that you use to produce a point on some auxiliary thing, and that point tells you the extension. But you have to kind of start with the abelian variety a priori, and you're looking for the abelian varieties using the extension. So anyway, it's that's kind of an issue. Okay, so I just maybe very fast wanted to just say one thing that allows you to get around this issue of trying to search for the abelian varieties given the extensions, but the extension, depends on the abelian variety, or at least depends in a not so difficult way on the abelian variety, is the following. This is what allows you, I'm just going to say the terminology. There's some kind of Taylor-Wiles hypothesis that says that you need to start with a residual representation that has a big image. And you don't know the abelian varieties ahead of time, so you need to know, in the argument of Taylor, you need to know how to start with a prime that's large enough where this Taylor-Wiles hypothesis will hold for all the abelian varieties you're interested in, even though you don't know them yet. So all you know about the abelian varieties is that they're conductors. And this lemma guarantees that you can choose such a prime. So the key point about this lemma is this bound is effective. This I write less than less or greater than just to mean this constant. So there's an effective prime. There's an effective way to produce a prime such that all the abelian varieties kind of have a residual representation satisfying this hypothesis that goes into the argument. This is actually not the real issue you could get around using this lemma, but this lemma is at the strength of an isogeny estimate only depending on the conductor of the abelian variety. which if that phrase isogeny estimate makes sense to you, then in the Mossel-Wusselt isogeny estimate, the famous one, the bound depends on the height of the abelian variety, and that's what you're looking for. You're looking for the height of the abelian variety, so you can't use that. But but in this case, this lemma is the strength of an isogeny estimate only depending on the conductor which you have in your hands. Okay, so I'm just gonna last line before I start maybe talking about more concrete things. So Taylor's argument can be started at a prime fixed ahead of time. That's just saying that in this lemma, you have some effective bound depending only on the conductor. And you're looking for the abelian variety, so you can't, you couldn't have used their heights in producing this bound. So you're not allowed to, that's what you're looking for. You're looking for the height, so it would be, you wouldn't be able to get started if you only had a bound in terms of the height, which would be the sort of thing given to you by any of the standard isogeny estimates or anything like that. Okay, so I just want to say in one line, the key issue actually is the fact that I phrased everything in terms of algorithms. And inside of Taylor's argument, he uses the theorem of Mordell, which is a local global principle. And that local global principle produces some point over some extension. And it's hard to say anything a priori about the extension. However, because I phrased everything in terms of algorithms, an algorithm has no issue finding such a point, because Mordell says a point exists, and an algorithm can run a search for the point once it knows it exists. Okay, it's like saying if you have a rank 1 elliptic or rank 10 elliptic curve and you found 9 points, but you are certain that the rank is 10, an algorithm is going to find you the 10th point eventually because you're certain. Because you so to speak, you prove the rank is 10, you're going to find that 10th point eventually. You can do it in style, you can do it quickly, but I'm just saying there is an algorithm that, the dumb algorithm will also work. Okay, now I'm going to get back to Earth a little bit and talk about hypergeometric abelian varieties, because so let me just scroll for a second. I'm going to talk about this curve, and I need to produce a family of these kinds of abelian surfaces over this curve so that I can apply this theorem to produce rational points on this curve, or to determine the rational points on that curve. All right, so I want to convince you, I just like this. This is not really relevant. I could skip the slide if I wanted to, but I want to convince you that hypergeometric abelian variety families are amazing, especially in the Mordell world. So I'm going to kind of circle this. Okay, so if I start with a hyperelliptic curve over Q bar, then there's a theorem of Bogomolov and Chinkel. So I only changed the color so it's kind of clear what the circle is. Okay, so there's a theorem of Bogomolov and Chinkel that says that a hyperelliptic curve over Q bar always admits an unramified cover, it's called C tilde, that admits a non-constant map to this one curve I started with way earlier, y squared equals x to the 6 plus 1. So let me just say that kind of this reduces the question of rational points on a hyperelliptic curve over a number field by, this is kind of a descent step, so this is not an issue from the point of view of the Mordell conjecture. You kind of start with, let's say, k points on C. You end up with having to determine L points on C tilde, where L is an explicit extension. So that's kind of a descent step, like you would do a 2 descent on an elliptic curve, for example, because it's an étale cover. So this reduces the question of, in that notation, k points on C to actually L points on C6, on the one curve C6. So kind of this Bogomolov-Chinkel theorem is amazing because it reduces the question of rational points on hyperelliptic curves over number fields to rational points on this single curve over number fields. And the point that I want to observe, interestingly, I think it wasn't observed by anyone even after Bogomolov and Chinkel, is that this one curve, this beautiful curve, is a Schmor curve. There's a hypergeometric family of abelian varieties over it, of abelian surfaces over it, where each of the abelian surfaces has quaternionic multiplication by an order in a particular quaternion algebra, the one of discriminant 6, the indefinite one. So it's indefinite and ramified at 2 and 3. So anyway, I find that very interesting. Somehow, this is kind of like you can imagine a generalized Fermat equation. So this is always over Q bar, but anyway, it's associated to the 266 triangle group, and the 266 triangle group is arithmetic. That's what's kind of witnessing the fact that the hypergeometric family over this curve has extra endomorphisms, has even more endomorphisms than a normal hypergeometric family. Okay, so I wanted to make this point, but now I'm just going to talk about this particular hypergeometric family that I use. So, right, so let's talk about this family in the last, I think, 10 minutes or 11 minutes. Okay, so the curve is x to the 6 plus 4y cubed equals 1. It's maybe not so crazy that if you kind of, so to speak, clear denominators, you see like a 6th power, a cube, and a 6th power here. So it's not so crazy that this thing would be associated to the 3, 6, 6 triangle group, but I'm writing 6, 3, 6 to be a little bit provocative. One reason I'm writing 6, 3, 6 is you can imagine the map x, y goes to x to the 6th in, oh my goodness, sorry, in P1. This is a Belian map, in fact. So it's ramified only over 0, 1, and infinity. And the ramification indices over 0, 1, and infinity are all 6s, 3s, and 6s, respectively. Oh, hopefully this didn't cut off, sorry. Yeah, anyway, so that's, you know, that's another indication of why I wrote this 6, 3, and 6. So actually, I would consider this kind of a, this is actually, I would consider like an unramified cover of not P1, but a stacky P1 where kind of 0 is like 1 over z mod 6 of a point, and 1 is like 1 over z mod 3 of a point, and infinity is like 1 over z mod 6 of a point. So it's an unramified cover of that thing, that weird stacky thing, which is actually hyperbolic. So it has a chance of being an unramified cover of it. Okay, so anyway, so I'm going to produce a family of abelian varieties over my curve x to the 6 plus 4y cubed equals 1. And I'm going to imagine, maybe I'll change notation here. So I'll call this alpha and beta. So my point is alpha comma beta, and it maps to alpha to the 6th. And I'm imagining calling alpha to the 6th lambda. So I said some kind of stacky P1, some kind of weird stuff is happening at 0, 1, and infinity. So just for the moment, throw out 0, 1, and infinity so that kind of, you know, you're working over P1 minus 0, 1, infinity. And you're going to kind of complete later on. You're going to extend this family of abelian varieties, or, you know, verify that the family of abelian varieties does not degenerate when you limit to 0, 1, and infinity. Okay, so for given a lambda in P1 minus 0, 1, infinity, I'm going to produce a family of curves, and I'm going to take the Jacobians and quotient the Jacobian by something to produce the abelian surfaces. So the family of curves is as follows. These numbers are chosen, are kind of given to me by the fact that I've chosen this particular triangle. There's some recipe, which I'm going to just show you. But anyway, I'm not going to actually go through it. So you consider the curves y to the 6th equals x to the 4th times 1 minus x cubed times 1 minus lambda times x. These are singular curves a priori. I think, yeah, they're singular curves, but you can consider their desingularizations and call those x lambda. So given a lambda, you produce this desingularization. So this gives you a family of curves x lambda. And this I've kind of shown you. So where do these exponents come from? You kind of are trying to produce. So you're trying to produce, in this case, the hypergeometric function 2f1 of, it just happens that I'm going to write down the parameters, I think, correctly. 5/6 lambda. You're trying to produce this hypergeometric function, this particular one, as a period integral of an abelian variety. And you're trying to produce kind of the minimal abelian variety with this period integral. So the parameters little a, little b, and little c are, you know, this is little a, this is little b, and this is little c, and they solve this set of equations. These are absolute value signs. So like, you know, this is like 1/6, 1/3, 1/6. Sorry, this is 6, 3, and 6. This is 1/6, 1/3, and 1/6. And if you plug in these values, they will solve this system of equations. And you can see, because I wrote absolute value signs, there's some ambiguities about signs. So actually there are multiple solutions. And those multiple solutions correspond to, well, there are identities between hypergeometric functions, but also there's a hypergeometric differential equation that has two solutions. Not just this particular one, but there's a sibling hypergeometric function. And it has different parameters. I'm not going to remember them correctly, but this one is 7/6, I think. It's like 2 minus c is always the sibling, I think. I think I got that right, yeah. So anyway, there's a sibling hypergeometric function that will also be a solution of these equations. So anyway, and so there's a particular identity. I think it's called Eulers Identity. Anyway, it's an integral identity involving an integral over a Pochhammer contour of something that looks like something that you get from this curve. So you integrate like dx times maybe the nth root of this right-hand side. So you're kind of integrating something in terms of y. Anyway, it's a great idea to produce a family of abelian varieties. I think this is due to Wolfhard. Yeah, so the genus of these curves, these desingularizations, is 3. Whereas I should have mentioned here, the genus of this curve is 4, I believe. So the genus of these curves is 3. And what I'm going to do is I'm going to take the Jacobians of these curves. That's going to be 3-dimensional abelian varieties. And I'm going to observe that actually there's like a one-dimensional piece which is not varying. So I'm going to get rid of the one-dimensional piece by modding out by it. And I'm going to end up with an abelian surface. Okay, so I start with a genus, start with a genus 3 curve. And okay, so here's the observation. So I rewrite the equation here. Y to the 6th equals, in my particular case, x to the 4th times 1 minus x cubed times 1 minus lambda x. Anytime I have a 6th power equals something not depending on y, I can map to the same curve where I take a cube, for example. Any divisor of 6, but cubes are the prudent ones to take. Take a cube equals the right-hand side. If I take a cube equals the right-hand side, and again, desingularize, then I get an elliptic curve. Why, intuitively speaking? If this were y cubed equals the right-hand side, well, I could eat the 4, and I could eat the 1 minus x cubed, so I would get x times 1 minus x. So I would get a cubic equals a quadratic, and that's an elliptic curve. And actually, that's a CM elliptic curve, in fact. So it's kind of modularized, not varying. It can't be varying because I'm going to try to give you a family of abelian varieties over a compact curve, and you're not going to find a family of elliptic curves over a compact curve because of moduli space considerations. So a non-isotrivial family of elliptic curves over a compact curve, I should say. Okay, so anyway, the moduli of the elliptic curve is not really varying. So, but anyway, there's a natural map to an elliptic curve, and so therefore the Jacobian of this, the desingularization eventually of this curve, which is a dimension 3 abelian variety, will map to this elliptic curve, and I can consider the kernel. I can consider the, so to speak, prim of this cover. So I can consider the connected component of the kernel of the map from the Jacobian to the elliptic curve. And that's going to give me a 2-dimensional abelian variety, 3 minus 1, because I modded up, I got rid of the elliptic curve part. So that gives me a family of abelian surfaces over P1 of the punctured P1 at the moment. But anyway, this gives me a family of abelian surfaces. Okay, so yeah, maybe I should have said this, but this is without these exponents. If I started, so to speak, with the recipe for infinity, infinity, infinity triangle groups, I would get something that looks a lot like, it's something like a twist of the famous Frey curves that Wiles used in his proof of Fermat. And that's a family of elliptic curves, and that has no chance of not degenerating at 0, 1, and infinity. And that's a real issue in the argument that gives Fermat, because that tells you that the conductors of the elliptic curves that you're using modularity for are huge, are growing with the putative solution of Fermat, of the Fermat equation. And so Wiles has to do something to reduce, so to speak, the conductors, and that's this level lowering argument. Or anyway, not just Wiles, but Ribbit. But anyway, that's this level lowering argument, the famous level lowering argument. So the point for me is that I'm trying to keep everything compact, so I have some a priori bound on conductors, and that's why I'm not kind of allowed to use. I'm not allowed to genuinely have punctures in my stack EP1, if that makes sense. So actually, I'm certainly not the first person to consider using even the hypergeometric family of abelian varieties in Diophantine questions. I think Darmon is, anyway, certainly Darmon is one of the people with absolutely the most significant work, but I think he might have introduced the use of the families of hypergeometric abelian varieties in Diophantine questions. And anyway, in his case, I think he has one of them, one of these things actually be punctured. So one of these things is infinity to run a Wiles type argument. But for me, it's deadly that I let the if I were to let the conductor blow up. Okay, so hopefully, anyway, that quick aside made sense. So I have 2 minutes left, so I'm going to quickly say. So I've produced a family of abelian surfaces. This family of abelian surfaces naturally has an extra endomorphism. So if I have y to the 6th equals something, I can multiply y by a 6th root of unity. And that's an automorphism of the curve downstairs. So when I desingularize, okay, it's still an automorphism. That automorphism passes to the Jacobian and passes to these abelian surfaces, in fact. So that's an extra, so that gives me a quadratic order inside the endomorphism ring of these abelian surfaces, which looks great because my theorem was about, the theorem from before was about abelian surfaces with an extra endomorphism. But these extra endomorphisms are not defined over my totally real fields. But this is actually a serious point. But anyway, so these endomorphisms are not defined over the totally real field, and I really need to work with Gauss representations valued in GL2. So this is not enough to run the argument. This is kind of saying that if I knew everything, if I had said imaginary CM field in the theorem, then I would be able to run the argument. But because I said totally real field, no chance. However, that's where the arithmeticity of the 366 triangle group comes in. I'm going to get one more endomorphism that will actually descend to the totally real field I started with. So that's where I say this triangle group is actually arithmetic. Okay, so there's an extra endomorphism, and I just mentioned the field of definition is crucial. So what I did is I looked at Gauss representations, and the last thing I want to say is I didn't write down the endomorphism explicitly. So the fact that the triangle group is arithmetic means that this endomorphism ring is, well, let's just say over C to be absolutely careful. It means that this endomorphism ring is a quaternion order. So there's more than just this Z adjoin zeta 3. And because it's a quaternion order, so to speak, I should be able to see that using the Tate conjecture, which is known for H1 of abelian varieties. So I should be able to see that from Faltings's theorem, and I should be able to see it at the level of Gauss representations. And that's how I produce this show that there is an extra endomorphism. So in the last second, I will say, so you can compute. So the zeta 6 endomorphism allows me to produce two or one two-dimensional Gauss representations over this imaginary CM extension, and there will be an extra endomorphism exactly when these Gauss representations have rational traces. And so what I'm saying down here is you can actually compute the traces of the Gauss representation because the curve I started with was x to the 6th plus 4y cubed equals 1. You can compute the zeta function of this curve over a finite field. This is the classic calculation due to Gauss. You take a sextic character and you compute some kind of Jacobi sum. So anyway, what ends up resulting is unsurprisingly, because these are hypergeometric Belian varieties, what ends up resulting is you get a hypergeometric finite field hypergeometric function as the trace function of your Gauss representations. And so the eta is kind of playing the role of 1/6. If you remember the parameters 1/6, 1/3, and 5/6 from before, this is kind of the sibling hypergeometric function, the other solution of the hypergeometric differential equation. And what you need is that these two finite field hypergeometric functions have are the same to get rational traces of your Gauss representation. And that is an identity. That's actually a little bit of a standard identity between finite field hypergeometric functions. But the key point is I found all this in the paper of Dane, Swisselier, Long, Swisher, and Tu, an amazing paper which does all this stuff. And yeah, so I just reverse engineered the equation of the curve from insisting that this identity, this is in terms of lambda, insisting that this identity holds. So that this thing has to equal this thing means that this thing has to be trivial, and this eta is a sextic character. So it means, for example, it will follow if this thing is a 6th power, which holds in this particular case. So I went through it a little bit quickly, but anyway, that's all I wanted to say. So thank you.
All right. Thank you so much. Let's thank the speaker. All right. And now, are there any questions? Okay, I guess I can start off. So this extra endomorphism that you got from the arithmeticity of the triangle group, are there other, is arithmetic the only condition under which you get this extra endomorphism, or are there other conditions as well?
Yeah. So the hypergeometric Belian varieties will in general have, I kind of rushed quickly all through this, unfortunately, but so these hypergeometric Belian varieties will be, so in this case, this capital N was 6. So the dimension in this case was 2, the Euler-Toscan function of 6. and they always, so they are phi of n dimensional abelian varieties, and they always have endomorphisms by this, the maximal order in Q adjoins zeta n. So this kind of rank phi of n ring. So this tells you that they're kind of GL2 type. So that's kind of the biggest they can be with varying moduli, unless they also have quaternionic multiplication. If that makes, that's kind of not a completely precise statement, but anyway, they you should kind of imagine like an abelian surface case. The abelian surface, in this case, I'm saying it has an endomorphism by an imaginary, this maximal order in the kind of the Eisenstein integers. It has endomorphisms by the Eisenstein integers, and if it has any more endomorphisms, it's because it either has quaternionic multiplication or because it has what's the word? Is CM, and it can't be CM because CM. Well, anyway, you wouldn't have a non-isotrivial family of CM abelian varieties over your curve, because CM, you know, there's the relevant kind of moduli space is a point, so they don't move. The moduli, there's no like continuous family of moduli. So so the only chance you have to actually have a varying family of abelian varieties is if you have an extra endomorphism to have quaternionic multiplication. And this, the fact that the statement that you have quaternionic multiplication exactly corresponds to arithmeticity, because arithmeticity is kind of a statement about, it's also a statement about quaternion algebras. So anyway, maybe it's not so surprising, but anyway, yes, it's very much arithmeticity that's the reason that you have more endomorphisms than just this kind of Z adjoins zeta. Yeah, and actually the endomorphism should be a square root 2 that I'm finding, but I didn't know how to write down the endomorphism just like in terms of, you know, for example, the coordinates of the curve. So I had to go this indirect route where I look at the Galois representations and see that there must be an endomorphism from a computation of traces of Galois representations. Yeah, but anyway, it should be a very concrete thing, this endomorphism that I'm producing.
So if they would not be arithmetic, then there would be problems, serious problems.
Yes, there would be serious problems. You would need to, so this, yeah, maybe I'll just say like, to see me struggle with the serious problems, in my PhD thesis in chapter 10, so in chapter 10, I start talking about, look, let's talk about, you know, hypergeometric families of abelian varieties over CM fields, over imaginary CM fields, and say what you can get out of this sort of argument. Now, the serious problem is the following. Actually, the potential modularity is known, maybe very, in my view, famously in recent years. The potential modularity kind of step that I'm using is known. Nothing is an issue there. So you get to some kind of list of automorphic L functions, not L functions of Hilbert modular forms, but L functions that are still kind of automorphic objects. But the issue is, so I said, let me just scroll up to show you the issue. What did I say? Anyway, so somewhere I say, for example, odd degree totally real field constantly. So the point is, actually, I think I write it. Yes, I write it here. So over an odd degree totally real field, over an odd degree totally real field, we know how to produce abelian varieties attached to all the L functions that we think should correspond to abelian varieties. Hopefully that makes sense. So we know how to produce abelian varieties attached to, in those cases, Hilbert modular forms. But over an imaginary CM field, it's pie in the sky still. You get the L functions that you expect. So to speak, you get an upper bound on the number of rational points. Let me just phrase it kind of vaguely. You get some kind of upper bound on the relevant rational points, or at least the relevant abelian varieties. And you need to know that that upper bound is sharp in a sense. And to know that the upper bound is sharp, you need to produce abelian varieties associated to the things that you expect come from abelian varieties. And over an odd degree totally real field, we know how to do that. That's a construction that I very quickly said they're all quotients of 1 Jacobian. So kind of, anyway, we know how to construct those abelian varieties in the particular case of odd degree totally real fields. Over a CM field, an imaginary CM field, we don't know how to do it. So yeah, in that chapter, I say assume that they exist in this chapter. So anyway, but it is a real issue. Yeah. And that's why, yeah, arithmeticity kind of bought me that I get at least one extra endomorphism over the totally real field I started with. But if I didn't have arithmeticity and I tried to use a hypergeometric family, indeed, I would have to assume the existence of abelian varieties. Yeah.
Actually, hypergeometric abelian variety which appears in Dorman program, all related with the non-arithmetic groups, I think.
Yeah. So probably not all, but indeed, the point is, I think the difference is that for Dorman, he takes one of these to be infinity.
Yeah.
Which is not so killer for him because he can use whiles and level lowering type arguments, but I always insist that I have a compact quotient of the upper half plane modular triangle group because I want an a priori bound on the conductor, and so yeah, that's the maybe key difference. But yeah, I should have maybe emphasized this hypergeometric family stuff is I really like it, but it's just a particular example of an application of, let's just say, yeah, I should scroll to where I say Hilbert modular variety of this theorem. So these Hilbert modular varieties contain tons of curves. This is kind of in this case, which I've summarized, the relevant moduli space is, so the dimension of, let me write it like h z adjoin root 2 is 2. It's a Hilbert modular, so to speak, surface, and these surfaces contain tons of curves because the surfaces are sit inside projective space in a way that misses only a finite set of points. So you can kind of imagine cutting them with hyperplanes or any hypersurfaces and getting compact curves, so long as the way you cut misses that finite set. So anyway, point is they contain tons of curves that are not coming from hypergeometric abelian varieties or anything like that, or from Shimura curves. So they contain tons of curves. I just don't know how to write them down in a clean way. So that's why the hypergeometric family came up, because I wanted an example of, an application of, for example, this or this. And that's where the hypergeometric families come up. So yeah.
I see, thanks.
Is there any other questions? Okay, so I have a more philosophical question. Can one do better if one doesn't ask for the actual rational points on the curve, but just the size of the set?
Oh, that's actually the entire issue. If you just, so you want a sharp bound, right?
A sharp bound, yes.
Yeah, that's the entire issue. So the reason is, imagine you had a way to produce a sharp bound. Like you had a way to produce, some magic algorithm, you type it in the computer and it produces the number of 15. So you know now that there are exactly 15 points on your curve. So now I'm going to say something that maybe sounds practically stupid, but anyway, is theoretically fine. So you know that there are exactly 15 points. So that means that you're sure that if you go and start plugging in every possible, imagine you say it for this particular curve here. There are exactly 15 points on this curve. So then you just start plugging in every possible x of larger and larger height. So you say, let's just take all the x's with, the numerator of at most 100 digits and denominator at most 100 digits, and just plug in and see when are they rational cubes. Okay, so you have all the patience in the world, and you just plug in all the rational numbers in order, so to speak. Eventually, you're going to find 15 rational points because you have this bound. And once you find 15 rational points, then you're done because you have a sharp bound. But if you ask for a not sharp bound, indeed, there are other ways. Faulting's even Raynaud, I should say, and okay, I should really say Spiro, and then using work of Raynaud, building on Faulting's, gave a way to upper bound after Faulting's proof the number of rational points on the curve, but that bound is not sharp. And then there are other ways. Vojta in his proof of Faulting's theorem gives another way to upper bound number of rational points, also not sharp. But yeah, actually the entire issue is getting a sharp, kind of knowing that a bound is sharp actually is the issue. So you can produce a bound and suspect that it's sharp, but once you prove that it's sharp, you've actually dealt with the whole thing. So hopefully that made sense. Yeah. Now, if you ask about computational complexity, then actually I haven't thought about it, but yeah, you can imagine that there's some magic algorithm that quickly gives you the answer 15, but then lets you toil for a long time to actually find the 15 rational points. I don't know. Yeah.
Great. Are there any other questions? All right. Well, if not, then let's thank Levent again.
Thanks, Levent, and thanks, Soumya,
Thank
for chairing it.
Yeah, thank you so much for the
you.
invitation also. Yeah, thank you. And thanks for coming, obviously.
Yeah, so Ganesh, are you there?
Yeah,